Now we will use a helium atom as a model to explain Heisenberg's idea about the exchange. So for illustration purposes, we're going to consider the excited state of helium. So let's consider 1s and 2s orbitals in two different scenarios. So I have an electron in the 1s orbital and an electron in the 2s orbital, and these two electrons have parallel spins or anti-parallel spins. So the first scenario is when these electrons have parallel spins, and the second scenario is when they have anti-parallel spins. Okay, so we're considering the excited state of helium atom, and we're thinking about two possibilities: to have two electrons in 1s and 2s orbitals with parallel spins and with anti-parallel spins. So if we were to write the Hamiltonian, the total Hamiltonian of this system, we would have three terms: H1, H2, and H3. The first Hamiltonian, H1, would be taking care of the kinetic energy of the first electron plus the potential energy term due to the interaction with the nucleus, and this electron is at position R1 with respect to the nucleus. The second Hamiltonian would take care of the kinetic energy of the second electron plus the potential energy due to the interaction with the nucleus, and this electron is located at position R2. The third term, H3, would be the interaction between the two electrons, H1, 2. So it would be a potential energy term, which is due to the electron-electron interaction with the distance between the electrons, R1, 2. And you can recall that the momentum operator in quantum mechanics is minus h bar over j gradient. J is square root minus 1. And kinetic energy operator is p hat square divided by twice the mass of the electron when it is operated on the electron. So if I write these Hamiltonians explicitly, so the first Hamiltonian operator, H1 hat, will be minus h bar square divided by 2 mass of the electron del 1 square, and then I have the potential energy, so it's atomic number Z e square divided by 4 pi epsilon 0, and the electron is located at position R1. And then the second Hamiltonian operator, H2, can be written as minus h bar square divided by twice the mass of the electron, del 2 square, minus z e square divided by 4 pi epsilon 0 R2. So that takes care of the potential energy due to the interaction with the nucleus. And then H12 operator would be the electron-electron interaction. It is plus e square divided by 4 pi epsilon 0 R12. And basically, we're considering these electrons as orbiting around the nucleus, which has a total charge plus z times e. And then I have one orbit around this at a distance r1. So I can say that I have a distance r1, so that's the radius of the first orbit. And then the second orbit is like this, and this is basically at a distance r2 with respect to the nucleus, and the distance between these two orbits is r12. So that's the relative position of the two electrons that are orbiting around the nucleus. I haven't done a very good job in drawing the second circle here, so these two circles are concentric, so just to make sure. Now here Z is my atomic number, and what I'm calling R12 is the difference between R1 and R2. So one thing I have to recall for this system is that when I consider the total electronic wave function of a system of electrons, this wave function has to be antisymmetric with respect to the interchange of two electrons. That's a statement of Pauli exclusion principle, basically. The total electronic wave function for a system of two electrons must be antisymmetric with respect to the interchange of two electrons. With respect to the interchange of two electrons. So this is a Pauli exclusion principle. So the total wave function, psi total, has to be the spin part, spin wave function, multiplied by the spatial wave function. That's how we can write it. And so if we have anti-symmetric spin, we must have symmetric spatial wave function. So let me note here, if I have an anti-symmetric spin wave function, this implies a symmetric spatial wave function. So that is to say, if you write the wave function for the anti-parallel spins, anti-symmetric spin wave function, then we have the symmetric version of the spatial wave function, which is a function of R1 and R2. It is 1 over square root 2, the wave function phi 1s at R1, phi 2s at R2, plus phi 2s, now we're exchanging electrons, R1, phi 1s, R2. So this is the symmetric combination of two atomic orbitals. So here I have phi 1s and phi 2s are 1s and 2s atomic orbitals. And R1 and R2 are the positions of electrons. R1, R2, position vectors of electrons 1 and 2. Okay, so this is one possibility: anti-symmetric spin, symmetric combination of spatial wave functions. And the other possibility is to have a symmetric spin. So if I have a symmetric spin wave function, then I would have and anti-symmetric spatial wave function. So this can be written as, now I have the symmetric spin, so this phi has to be anti-symmetric as a function of R1 and R2, and this is going to be equal to the anti-symmetric combination of the wave functions, which is a 1 over square root 2 phi 1s R1 phi 2s R2 minus phi 2s R1 phi 1s R2. So this is anti-symmetric with respect to the exchange of electrons. So this would be the second possibility for the combinations of the wave functions, spatial wave functions. Now, if I write the total energy of the system, you can see here it's done explicitly. So I have the total wave function phi R1 R2, and the expectation value of the total Hamiltonian operator will give me the total energy of the system. So this is basically calculating the total energy, which is expectation value of the Hamiltonian. Now, if we start writing this Hamiltonian, so we have either symmetric or anti-symmetric combinations. So phi 1s R1, phi 2s R2 plus or minus phi 2s R1, phi 1s R2. The symmetric combination, the plus will imply anti-symmetric spin. So this plus will imply anti-symmetric spin. So let me lock this. All right, so this is going to imply anti-symmetric spin. The minus sign will imply the symmetric spin configuration. So I'm writing the total wave function first, and then the total Hamiltonian operator, h1 plus h2 plus h12, and then the total wave function again in the expectation value. So if I start doing this, the first term that I will encounter will be phi 1s R1, phi 2s R2 operating on h1. So here I want to check something, so let's put a remark here. So if you look at the first term, we see that it is 1 over 2 phi 1s R1, phi 2s R2 acting on the first Hamiltonian operator phi 1s R1, phi 2s R2. So if you write this, what this means, this is actually 1 over 2 integral over all space. This is using Dirac's bracket notation. You have phi 1s complex conjugate R1, phi 2s complex conjugate R2, Hamiltonian operator acting on phi 1s, phi 2s. Hamiltonian operator 1, H1, was basically minus h bar square over 2m del square minus ze square over 4 pi epsilon 0 R1. So the derivative of a function of R2 with respect to R1 will give you 0. So this operator actually does not act on the electron at R2. So basically we have phi 2s R2 unaffected by this operator, and then the operator H1 hat will operate on phi 1s r1. So this integral over all space of phi 2s r2, so this will be phi 2s r2 square. When you integrate this over all r2 values, this is going to give us 1. So this part will give us a 1. That's the normalization of the probability distribution function. So this will give us basically 1 over 2 integral over all space phi 1s star r1 Hamiltonian operator acting on phi 1s r1. So you can see that this is actually phi 1s r1 h1 phi 1s r1 with this 1 over 2 here. So that's basically what is done here. So you can see that for the first term, phi 1s r1, phi 2s r2, acting on h1 and the same term will only give me the first term that I see here, which is phi 1s r1, h1, phi 1s r1. And when I go to the next term, phi 2s r1, phi 1s r2, again, the r2 terms will disappear and I will have phi 2s r1, h1, phi 2s r1. And we continue with the next term, which is the second Hamiltonian operator. The same argument applies. Now this time the only ones that survive is the functions of R2. So phi 1s R2 in the first term and phi 2s R2 in the second term. And then the H12 operator will have, because it depends on both R1 and R2, it's the difference between R1 and R2, will act on all terms, and it will give us 4 possible configurations. One includes phi 1s R1, phi 2s R2, phi 2s R1, phi 1s R2, and the second one, phi 1s R1, phi 2s R2, and phi 2s R1, phi 1s R2. So if you look at these terms and what they mean, so we realize that the first term that I'm showing in blue here, when you have the electron in the 1s orbital at R1, and when you have the electron in the 1s orbital at R2, we're calculating its energy. So this E1 is taking care of the 1s orbital energy, and E2 is taking care of the 2s orbital energy. So that's basically what I note here. And this other term, phi 1s R1, phi 2s R2, first electron is in position R1, second in R2. So we're looking at the Coulomb interaction between these two electrons. So K is my Coulomb term, and then I have cross terms where I have phi 1s R1, phi 2s R2, and phi 2s R1, phi 1s R2. So this is the exchange of electrons, the cross terms, that gives me this J integral. So you can see that the total energy is the sum of these 4 terms: 1s orbital energy, 2s orbital energy, Coulomb energy, exchange energy is what we call J, and there's a plus or minus. Plus means you have symmetric combination of spatial wave functions, which means anti-symmetric combination of spins, so anti-parallel, and minus means parallel spins. Now, so once again, you can see that what I'm calling E1 here is actually one of these terms, because there's a 1 over 2 here. So phi 1s R1 H1 phi 1s R1 is equal to phi 1s R2 H2 phi 1s R2. So the same two terms will give me 2E1 divided by 2 gives me the total energy E1. And the same thing is true for E2. So this is the 1s orbital energy is E1, and the 2s orbital energy is fixed, it's E2. And then I have the Coulomb interaction between electrons. When the electron is in R1, 1s electron in R1, 2s electron in R2, and then I have 2s electron in R1, 1s electron in R2. It gives me the same result. And then I have 1s electron in R1, 2s electron in R2, 2s electron in R1, 1s electron in R2. So these are the cross terms. So these are the cross terms in the energy calculation. So I noticed that when I write this total energy, E1 plus E2 plus K plus J. So what happens if J is positive for the anti-parallel combination of these two electrons? Well, I see that I will have E1 plus E2 plus K plus J, that is for anti-parallel, and E1 plus E2 plus K minus J for the parallel configuration. Parallel configuration has the minus sign. So in this case, if you calculate these energies, the parallel one has lower energy compared to the anti-parallel one. So we find that J positive favors ferromagnetic alignment, a parallel spins. On the other hand, if I do the same exercise for a negative outcome of this integral, this would give me E1 plus E2 plus K, and then because J is negative, when I say plus J, it's going to be minus absolute value of J, so this is going to be a low energy. And this one, E1 plus E2 plus K minus J, is actually plus absolute value of J. Minus minus will become plus. So therefore, in this case, I find that the anti-parallel configuration has lower energy compared to the parallel configuration. So I conclude that J negative favors anti-parallel combination of spins. All right. So basically, we have worked on the quantum mechanical description of the helium atom in the excited state. We have one electron in 1s orbital, another electron in the 2s orbital. They can have either parallel or anti-parallel spins. When we consider the total Hamiltonian operator, it has a contribution from kinetic energy and potential energy with respect to nucleus at R1. So that's the 1s electron at R1. And then we have kinetic energy plus potential energy contribution with respect to nucleus at R2. And then there is the Coulomb energy due to electron-electron interactions. So if we write these Hamiltonian operators explicitly, this is what they would look like. And the total electronic wave function must be anti-symmetric with respect to exchange of electrons. That is Pauli exclusion principle. So if you have the spin part and the spatial part giving you the total electronic wave function, when we have anti-symmetric spin, we need symmetric combination of atomic orbitals. And when we have symmetric spin, we have anti-symmetric combination of atomic orbitals. The way we calculate the total energy of the system, again using bracket notation, is by calculating the expectation value of the total Hamiltonian operator. And here I have shown you that the H1 operator only acts on electrons at position R1, and H2 operator only acts on electrons at position R2. So if we write the energy explicitly, we see that it consists of 4 terms: E1, which is the 1s orbital energy, E2, the 2s orbital energy, K, which is the Coulomb energy for electron-electron interactions, and J, that is the cross term. So when you have 1s electron in R1, 2s electron in R2, crossed with 2s electron R1, 1s electron R2. So the electrons exchange positions, and then we have an energy term here, that's J. And we see that the total energy has a plus J for anti-parallel spins and a minus J for parallel spins. And once again, if you have a J value that is positive, For the anti-parallel configuration, this increases the energy. For the parallel configuration, it decreases the energy. So J positive favors parallel spins, or we can call this ferromagnetic ordering. On the other hand, when we have J negative, you can see that it's the opposite situation. The anti-parallel energy is lower than the parallel energy. So J less than 0 favors anti-parallel spins or anti-ferromagnetic ordering.